So I've got the chassis all cleaned up. All the switches have been removed. All the terminals have been removed. They've all been individually cleaned. Everything's been put back. When the chassis was cleaned, also when everything was removed, I used some of the spray wax to wax up the paint and provide some protection. I've left this one off the CRL knob here, and the reason I did that is because obviously this knob is coming out so that we can make the repairs to bring the 10 segments back into specification. Obviously, we already know from our previous testing it is out of specification, and we're going to be working on that next and order the parts we need to fix it. So here goes. Because we have more than enough bus bar to work with, it's much safer to simply cut the bus bar just before the terminals than it is to try and desolder it from within the unit. Then once this is removed from the unit, we could clean up those terminals, bend a new piece of that bus bar, and reattach it later. So that's what I did. I clipped them both off. Now this unit could come out of here and be tested, and we could test those out and replace what's necessary to bring this back up to specification. With the CRL knob now removed, I've put the dial back on, so I'm able to obviously cycle through. I'm able to cycle through the potentiometer easily. Used a bit of deoxit to clean up the potentiometer. The potentiometer is a 1200 ohm potentiometer with a little slack on either side. I believe it's 1250. Schematic calls out for 1200, and basically what that is looking for corresponds to the 0 to 1.2 on here. So when calibrating, that's why it calls out the 550 for this dial. So basically what you're doing is, as long as the sweep is good on that, you're getting it into the center of that, and that becomes the center point for this dial. So that's the secret to that. We hook this up to the IM11 and make sure we get a nice sweep on that potentiometer, and that should be good. You know, that will be sufficient. I cleaned up the contacts pretty nicely with the deoxit as well for this. Not that I had any problem with the contacts, but presented the opportunity with it removed. And we're going to go through with the fluke to each one of these resistors. I already know some of them are bad. I've done some spot checks. The tolerance for this is 5 ohms. Some of them are well out of 5 ohms. 5 ohms represents 1/2 of 1% of 1,000. Obviously, the new ones that go in will be well under 5 ohms of tolerance, which should make this even more precise than Heathkit originally called out for. I don't anticipate, obviously, any great amount of resistance incurred between the connections or in the switch itself. Not really concerned about that. I think if we get an entire ohm through the whole thing, I would be thoroughly amazed. So the problem is in the resistors. I'm going to go through them, and then we'll look at the totals and the compound totals and see what we got before we do anything. Besides, I got to order more parts anyway. With the CRL dial removed, what I wanted to know is how much voltage and current passes through those resistors. I wanted to see how much power those resistors are dissipating. So when I order the new resistors, I make sure that they are appropriate. And I was able to check my work. What I found was this, is that, you know, at 1K, because I did it in 1K intervals on this box, and the box is obviously not calibrated like the other one, but it's close enough to have my current meter here that ran between the resistor box, and then I got my voltmeter that wrapped around and read those readings. And what I got is you know, starting at 1K, you could see the voltage neg 12.5 at 12.4 milliamps. I had a dissipation of 0.155, keeping in mind that the 1/10 of a watt was being dissipated through one resistor, right? Not a lot of wattage, but still through one resistor, but no problem for the resistors that I'm getting. Noting that with each one, the dissipation, not only is it getting lower, but it's through multiple resistors, so it's even better. But in checking my math and going backwards, you'll find that when you do the calculation for resistance, you'll find that we could actually see what the resistance was of my resistor box. And you'll find it's not entirely accurate because this box has not been calibrated yet. See, 1008, 2004, and then all of a sudden 3 becomes 2599, and before it becomes 3616. But still, what it shows is that with half-watt resistors, especially ones with those coefficients, we're going to be absolutely fine. We finally make our way up to 10K, goes as high as 11 or 12K for a maximum of, I believe, 25 volts. I didn't bother checking at that point, but we could see 23.46 at 2.35 milliamps, brings us about 9982 ohms, and dissipates about 0.055 watts through 10 1K resistors. So not a lot of power is being dissipated through here. Pretty good. No problems at all. And because we're already thorough, it's worth noting that the selector knob for the multiples was also checked. We had adequate room with the CRL knob removed to get behind there and check those values right here. These are multiples of 90, all the way down to 1 is the configuration used in this particular device. I found some of them to be okay, within 0.5%, as you can see demonstrated. Some of them were not. Unfortunately, the one I really wanted to be good was the 9 ohm, and the 9 ohm was just out of range, as you can see here. 9.2 with the correction, we're at 8.8. We needed 8.95 to be in tolerance. And I said, you know what, forget about it. We're ordering all these 0.1%. We could do this too. You can't get a 9 ohm resistor. So what I ended up doing is, again, I got 327s, and that got me down to 9 ohms at 0.1%. That should be good. This went into the big order that went out. There was a big order that was purchased that should be arriving in a couple of days that should cover all this, the capacitors, and more. I should quickly talk about this switch right here. Just to point out, most of these features are routing. These are not calibrated. These just move circuits. The only one I really want to discuss is this, the CD and the CDQ. These have a very specific capacitor behind them. These are capacitors that are apt to really go bad, so I don't believe they are bad. I will test those two capacitors, and if they're bad, I'll replace them. This is so far down the path of things that I need to be working right now that I'm not overly concerned with it yet. So I'm not worried about this circuit yet. This is sort of an end game sort of thing right here. What's really important is down here, not up here. Remember that with some of the other work, I got to work on this generator stuff and some of the rectifier stuff on the bottom. So of less importance, the stuff is in there, will be looked at. It's just not on top of the list right now. When I put in the order for the components, I realized that I did not order any of these 0.02 capacitors. The ones that you could see here, the black ones from these pyramids. Also this 0.005 up here. So what I did was I said, okay, fine, I didn't order them. Let me pull these out of circuit, check them for capacitance, and then torture test them on the IT11. They're rated for 600. The IT11 does 600, so very good. I have a copy of the schematic here. So we're looking at 7 in all, just to give you how it all turned out. All of them turned out to be good as a measure of capacitance. All of them turned out to be good as far as leak down. They probably could have gone beyond 600 if that was even possible. So surprisingly, all those capacitors were perfect. They were put back in circuit, and while I was down there with the capacitors disconnected, taking apart a lot of this circuit, I was able to get and measure a lot of the resistors that were down there as well. Some of them you really had to break out of the circuit. You can see the NIC that I posted there. Just can't be done unless you disconnect all sorts of things. Wasn't overly concerned. And the only resistor I found that concerns me is that 4.7 meg that's sitting right there across, and that should be right up there, and that's reading 5.4 meg, and that can't be right. So from all the resistors I've measured thus far, I found the one resistor that requires replacing. That gives me a good sign that this machine probably wasn't very tired, didn't get a lot of abuse. But I've ordered, as far as the electrolytic capacitors, obviously this 2020, this one over here, and this can down here will be replaced, although the can itself will remain. I'm going to do a cosmetic replacement with another piece of board down here, disconnect the can from circuit and put the two caps under here, leaving the can actually in the chassis. So when those parts arrive, that work will be done as well. Also, this appears to be a diode of sorts. It's a very weird looking old school diode. Shows also to be in the diagram as a diode, labeled as a silicone diode. You can see the Model 51G diode back here, right? And that's shown over here as a silicone diode. And then I also have a diode down here, which actually has a screw adjustment on top. And that is labeled in here as a meter rectifier or diode, right? So that diode is over there. And then we have, in the absence of our regular tube full bridge rectifier, obviously for heat reasons, they put a selenium rectifier here. And that uses this schematic diagram right here. This is a 150 milliamp bridge rectifier, right? So we actually have three diodes in here. That one, that silicone one, the strange looking one, and then that little one with the screw adjustment on it. So interesting stuff. Interesting stuff indeed. So I figure while we're waiting for parts, let's at least look at the AC generator, which is the foray into the AC side of this unit, right? And what we have is the AC generator level, which is tied to the power on off switch. And this switch right here, which turns on and off the AC generator by switching to AC internal, I believe. So right now, the generator is off, and I have it on the lowest setting. We'll go through this. So by switching this switch, I have it on external, and now I have it to internal, and I have it on the lowest setting. So as I turn this knob over here, you can see the generator coming up. Now let me just check. If I go to external, interesting, the generator stays on when you switch to external, but I imagine it uses the external reference. The generator stays warm though, so it stays idle. But just to show, here's the generator knob up here, setting the level of the generator. Looks like a nice sine wave. Interesting note is that in looking at the sine wave, having not touched it after all these years, when we look at, you know, they have a roundabout way of setting this frequency to 1 kilohertz, or checking the frequency. On my modern oscilloscope, I don't have to do any of that. It tells me, and if you look at it, it's 1.01 kilohertz. Obviously, I could do better. I could get that to 1 kilohertz. It really doesn't matter, you know. But wow, you know, somebody really took the time to set this thing really close to 1,000 hertz. And did a really good job. And after all these years, you know, there's a trimmer capacitor right there that you could see. Try and focus in on that. That trimmer capacitor right there is what sets the frequency. But this frequency is pretty good. I'm quite amazed that this thing is so close to 1,000 hertz after all this time. But at least as far as the workings of the circuitry, we could say that the AC generator is working, the intensity of the AC generator is working. A little bit of jitter on there, you know, but then I haven't replaced any of the electrolytic capacitors either, right? So I haven't gone through the diode, so I'm not really overly concerned about that right now. But I am impressed as far as the operation of this circuit. So pretty good. That's the AC generator side of this unit up here. Also, for the purposes of this video, I want to point out that with the potentiometer turned all the way to the maximum position, that the period RMS voltage sits around 520 millivolts, and the peak to peak is at 1.5 volts for this sine wave. So we'll see if that's the same voltage once the capacitors have been replaced in this unit. Each of the 1K resistors will be tested. Try that again. Each of the 1K resistors will be tested. I've removed one of the 1K resistors, and what I've done is I've done that so I could size it up see how I want it to be fit on there. Since I'm going to repeat this process 10 times, this is what I'm going for. I know the other one will slide through onto the next rail. I've cut the second one away to accomplish that, right? Now that I got that, I'm going to take it out and I'm going to bend them so they all match up just like that. So I'm going to take these, test 10 of them, bend 10 of them, and then cut them out and put them all in. So that's obviously what we're going for. Thought I'd make a quick movie of the progress here as I make my way along. Here are the 1K 0.1% that are slowly replacing the old ones. You can see as I go along, I'm just slowly removing them, replacing them with the new ones. I've made a small temporary jig with a pair of pliers so that they're bent the same way, sort of have a nice symmetrical look to them. Testing it as I go along with the multimeter. Now we have them all installed. It's time to test everything out through the switch. Our first test will forego the potentiometer. We're just testing the switch itself, so we'll come right off this tap before it goes through here. But this is all of the new 1Ks replacing the old ones that have been removed. They're right here. So here we go with our test, bypassing the potentiometer. Find out if all our efforts were worth it. Point out, because of this alligator clip mess, we show 1 ohm of resistance before we even get started going through this. So just to point that out, right? So we click from 0 to 1, and we've got 1K. Two, 3, 4, 5. I mean, everything else at this point is, the values are so negligible, they're not even worth reading. 6, 7, 8, 9. Right, that's the top already. And the rest of it would be from that potentiometer. So this came out very nicely. We're going to go with that. All of the electrolytic capacitors have been replaced. The duo over here, the double, was replaced by 2 separate 20s. This 100 over here has been replaced by a much smaller but higher rated 100 by this rectifier, and the double 1000 has been replaced by the 1000. The can is still up on top. I've just bypassed it. It's been clipped and there's a wrap around here. They give me really short leads. I was pretty pissed off for these Nichicons, so I had to make a this tie-off lead going to here. I had some problems with that, but it's bypassed from the old capacitor and everything is done. All of these are going to have to be redone too to bring it to specification, like the other ones were. They're out of spec, and when I look at all the connections and all the work that's going to be required to remove them, I thought to myself, and I said, it'll take longer, but it'll probably be safer, or at least it will appear to be at first, to remove, just simply remove these tubes. I could probably do the work on this inside the chassis. So what I'm going to do is I'm going to at least start on the outer rung, because in doing so, it'll give me a lot more room, and I think I could replace these without taking it out. So that's what I'm going to do with this one. Remember, some of these are combination ones, like 9 ohm, like 327s in parallel are going to give me 9 ohm. But other than that, I feel like there are just so many wires going to this and so much bus bar that it may cause more damage than good to try and remove this. This one had 2 connections. It was in the corner, and the amount of work that needed to be done was such that it was better to remove than leave in place. And by the same token, this one is better to leave in place than it is to remove. So at least for now, I've made my choice. The work is going to be done inside the cabinet. And here is my custom 0.1% 9 ohm resistor, which is 3 27 ohm resistors tied together in parallel. And I've measured it. It is a perfect 9 ohm. That'll be going in. So all the work has been done on this outer portion of the rotary. It turns out, when I check my notes, this 9K here measured perfectly 9K. And I only ordered one 9K for the inner one over here. So I left it. So that 9K is good. It's left in place. You could see here this 9 ohm, which is a combination of 3. I can't really focus on it. You see the 3 I mentioned earlier, that's in. There's the 1 ohm. Everything is good on this outer rung. It's all been tested. I got a couple to do on the inside, and that should be it. Okay, everything's been done. If it hasn't been replaced, it is well within tolerance. We'll take a final reading, and then we'll put our CRL knob back in because that's already been tested. All the measurements have been redone in black and show a perfect reading for all of these values. Okay, here we have the CRL knob back in, bus bar reconnected. This is our multiplication knob right here. This is, or range knob, depending on how you look at it. This is already done as well. So everything back here is done. These appear to be okay for now. We'll go into these a bit later if necessary, but if these need to be replaced, these capacitors, we're not talking about a lot of work like the other stuff. This is minor work, so we'll assume everything's okay, and we will now bring this back into the normal operating position and start our procedures that we would do post-op. So we move into the next phase now with our work on this impedance bridge.